FIG meeting. He was one of the original FIG implementers back when the FIG implementation team was implementing figFORTH. And he'll say a few words about that and a few words about his implementation.
I did indeed. Good morning, everybody. It's nice to see some old friends again and meet some new friends. When Kevin asked me to give this talk, I thought, well, that's a neat subject, but where's the content going to come from? Because all this work was done 30 years ago, and I threw out all the PACE documentation about 20 years ago. But fortunately, I did save the source listing, and on your website, I found the glossary and the implementation manual. Dr. Ting's book was particularly helpful, and it turned out that bitsavers.com has a bunch of PACE manuals, so I gathered all this material together and spent a weekend refamiliarizing myself. And it's amazing how fast stuff comes back to you when you have the right triggers. So here we are. I'm going to talk about the PACE figFORTH implementation and focusing in particular on adapting the figFORTH glossary to a word addressing computer. As you may recall, the FIG implementation project aimed to create 9 reference implementations of a common specification, which was the figFORTH glossary. And it wasn't actually cast in stone. It evolved quite a bit during the course of the project. And we released these implementations at the West Coast Computer Fair in 1979. The first thing I had to wrestle with were some major design issues, like how are the data that the fourth machine deals with going to be represented in the computer memory, and what's the connection going to be between the fourth virtual machine and the actual hardware. Well, some of the choices were obvious, since fourth traditionally was using a 16-bit stack, then I'd have one stack cell per machine word, and the stack pointers would all be native machine addresses, and you just change them by 1 to push or pop an element on the stack. And likewise, one dictionary field per 16-bit word, so the compiler stores code field addresses, in successive machine words, and the inner interpreter just deals with native machine addresses. So all that was pretty obvious. But the more difficult question was what to do about text data. In those days, ASCII was the standard that we used, and it was a 7-bit code, so you could fit 2 characters into one word if you wanted, or you could unpack them and just have 1 character per word and have the rest of the bits be 0. One character per word is actually probably the best choice today because storage has gone down in cost per bit by much more than a factor of the 2 you would lose by unpacking the data. And it allows internationalization of word names because you can use things like UTF-16 Unicode characters. And the biggest advantage of having 1 character per word is you can give each character in the text its own unique machine address. The PACE, the least amount of memory that it could address was 1 word, not 1 byte. So it's a big advantage to have a unique address for each character. Can't do that with 2. There could be issues with data exchange depending on where the rest of the world was. We traded floppies back and forth, and most of the time the floppies were, of course, had ASCII text on them, and the I/O subsystem that I had at the time delivered packed character data. It had to do that because if you read in a program off the disk, you wouldn't want them to unpack the machine instructions. So you might have to have special unpacking in the I/O routines, but that wouldn't be too bad. What I actually chose to do was have 2 characters per word because it was the most efficient use of the storage that was kind of expensive at the time, and we didn't have any Unicode standard or even ISO 8859. And a minor technical advantage was that it allowed paren find to compare 2 bytes at a time. Paren find is the dictionary search primitive in figFORTH, and it gets called a lot when you're compiling, so it's important for it to be reasonably efficient because it has to do a linear search in a vocabulary. And that can add up when your dictionary gets large. And I just used the existing I/O subsystem, which delivered packed characters. Well, what are some of the problems and implications of doing it that way? In order to process characters of text, you need to have a way to address each byte of a word. I can't, byte addressing machines wouldn't have that problem, but I did. So I was forced to add an abstract address mechanism in order to access these bytes. How does that actually work? I added 2 new conversion words. The word byte took a machine address on a stack and converted it to a byte address just by multiplying by 2. And I had to add that about 15 times in the pre-compiled figFORTH nucleus. And the converse word cell takes a byte address on the stack and divides it by 2, and you get back the address of the word that the byte is in. And I used that about 7 times. It turns out I had to modify 14 words in the dictionary to take byte addresses, and some of them are kind of obvious of cfetch and cstore and cmove all have to, since they operate on bytes, they have to be able to address the byte. And most of the rest have to do with text handling in one way or another. There's some of the details. I mentioned the cfetch, cstore, cmove. Count is an address that prepares, it takes the address of a text which has a leading count byte and splits off the count byte and the address of the remaining text. So it has to return a byte address. Enclose is a text scanning primitive in figFORTH that uses byte addresses. Expect also. Hold is a variable that's used for formatting numeric output. And if it points to a character, the next character you put in, it has to have a byte address also. The paren line is used for finding data in the input. Number is used for numeric formatting output. Toggle is kind of analogous to cstore. Exclusivores a given byte at a byte address, so it has to have a byte address. Traverse is a primitive that scans through the name field of a word in the dictionary, and it looks for the special start or stop bit that we use to deal with the variable length names. And that has to go byte at a time, so it needs to deal with byte addresses. And dash trailing removes trailing blanks from a string. That has to deal with byte addresses. And finally, a type, it's kind of the opposite of count. It takes a byte address and a byte count and sends it to the terminal. Pound greater than is a cleanup word that's used after numeric output. And it's typically used just before type, so it has to produce the same arguments on the stack the type expects. But most of the time, word addresses are used. The stack pointers use word addresses. The addresses that the inner interpreter deals with are all native word addresses. Fetch and store and all the operands that deal with 16-bit data just use native word addresses. The dictionary pointer, all the dictionary fields are words. Also, the areas in memory, the buffers that we use, TIB is an input buffer, PAD is an output buffer, and the disk buffers, can use word addresses for those. And in fact, most words in the glossary, all but the 14 that I showed, just can be reinterpreted to use the native word addresses. There's some real problems with the byte addressing scheme. First of all, it creates a 32K word barrier in memory, because if you have a word whose address is greater than 32K, when you double it to convert it to a byte address, it gets aliased back to bytes in low memory. So byte addressing doesn't work too well above that 32K word barrier. Well, that was a problem we wished we had, because most systems had about 16K bytes even, not let alone words. And really no worse off than with a byte address machine with its 64K address space. You still have 64K bytes in the 32K words. But the bigger problem is that it led to a schizophrenic API, because now in the API there are two different address types. There's the byte addresses and the native cell addresses. And there's no strong typing in the language that keeps you from using the wrong one in the wrong place. You have to remember those slides that I showed as to what goes where. And this puts a burden on the programmer to remember, what type of address you're working with on the stack at a given time. Okay, so having decided on the character representation, talk about the mapping of the fourth machine onto the actual PACE hardware. So we'll start with an overview of the PACE architecture. As I said, its unit of addressing is one 16-bit word, and in fact all machine instructions were one word long. There's no inline addresses or extension fields or any of that. Therefore, all memory effective addresses had to be derived by adding a short offset in the instruction onto some sort of base address. Or for particular instructions could also factor indirectly from that effective address. It had memory mapped in bit banging I/O, and there was a 6-level priority interrupt system. Here's a programmer's model. There's 4 16-bit accumulators, 16-bit program counter, a 10-word on-chip stack, and a number of flags. The most important for programming use are the link, carry, and overflow flag, which are set as a result of arithmetic and logical instructions. It can also be set and tested directly. I don't have time to go over the full instruction set, but I do want to talk about the address modes. So here's a typical memory reference instruction. You have a 6-bit opcode, a 2-bit field that specifies the address mode, and 8-bit displacement. And that allows you to directly address 4 different pages in memory. If the address mode is 0, then the displacement becomes an absolute address in low memory. So you have a memory base page, either the first 256 words, or alternatively the first 128 and the last 128, and that depends on the setting of a pin on the PACE chip. If the address mode is 1, then the displacement is a signed displacement from the current program counter value. If the address mode is 2 or 3, then it's a signed displacement from the value in accumulator 2 or 3 respectively. All the registers can have some common capabilities. You can move data to or from the flags register, the top of the internal stack. Any of the other 3 registers are memory. You can test memory, compare with memory equality, compare with memory, add an operand from memory, load an immediate operand from the instruction or complement, or add an immediate. You can add with or without carry and or exclusive OR from any of the other registers, and also shift and rotate left or right by an arbitrary bit count. In addition, some registers had some special capabilities. The accumulator 0 was the most powerful. You could test it for 0, non-zero, positive, negative, and also the 3 least significant bits for some reason. And it had additional operations with memory operands besides just add. You could and or subtract, decimal add, have greater than or mask test and a load a byte. And accumulator 0 was the only register that you could use indirect addressing to load or store with. Accumulators 2 and 3, as I mentioned, serve as base registers for memory access. So how did I allocate these resources to the fourth machine? Well, I decided that the accumulator 0, since it's had all these special arithmetic and testing properties, that should just be a working accumulator. Don't want to tie it up with pointers. The next most powerful registers were the index registers. I thought that the parameter stack is used so much that it would be good to have that live in an index register. So accumulator 3 became the stack pointer. The other index register I assigned to W, it doesn't really tie up the index register all the time because W is a volatile quantity. It gets reset every time through next, so it's not taking up too much resource. And a lot of code words like to have access to W, to access their data. And the least powerful register, accumulator 1, I put the instruction pointer there, and that forced the return pointer, return stack pointer to be in memory page 0, along with the user pointer. And the internal stack got used as a scratch area. Well, you might wonder, could it have been used as a parameter or return stack instead for efficiency? Well, the problem was that it's only 10 words deep, not really deep enough. Only the top word is accessible to copy from other registers. It's not easily extended into memory. It can be done, but you'd have to enable a stack full and empty interrupts and have a service routine to handle them. And if you got a stack full interrupt, for example, you couldn't just push all the data out the bottom of the internal stack into memory. No, you have to float the words off the top one by one and store them in memory in the right order. So that was just too complicated. So I decided that the on-chip stack is going to be used for register saving, JSRs, and interrupts in case your installation requires it to run with interrupts enabled for I/O or whatever. So how do these choices work out in the code? Here's a snippet of the beginning of the figFORTH dictionary, which starts with the word lit. And traditionally in our model, that falls through into next eventually. Next is 4 instructions, not too bad. And you notice that the last word jumps indirectly through W. That W holds the code address from the code field address in the dictionary. And so that's why it's good to have W in an index register so you can do that. And put and push each add 1 instruction. There's a number of places where you have to increment or decrement a pointer, and it'd be nice to have auto increment and auto decrement addressing, but we didn't have that, so that's the next best thing. As for the okay, almost finished. As for the return pointer, it's happy in low memory because you can get data to and from through index register 0 by means of indirect addressing. There's also instructions that can increment or decrement a word in low memory, so that serves for pushing and popping. So to summarize, the PACE implementation split the figFORTH glossary's concept of a single address type into 2. Most addresses in the fourth virtual machine were native word addresses allowing efficient execution, and abstract byte addresses were used for PAX text handling and for compatibility with 8-bit algorithms. Well, that's it. Thank you very much. Have any questions?
Did you implement an assembler?
That's another story. Yes, I did. I'm sure, I think I did, yes. But I don't have the source, the listening for that.
So it's lost to
it's lost, but
time.
But it'd be easy enough to do again because there's not that many instructions.
By the way,
It's pretty simple instructions.
When you get a question, if you're a speaker, when you get a question, repeat the question because otherwise it's not going to get onto the record. Well, Eric took that.